Okay, so welcome to lecture 4. Today is going to be kind of a grab bag of topics as it's sort of officially the last lecture on data collection. And so we're going to, first we're going to do a little bit more technical stuff, sort of left over from last time, and then we're going to zoom out away from polling to sort of how these similar challenges show up in other contexts. Before we get started, are there any questions from last time? Nope. Okay, cool. Okay, so like I said, the first plan for today is some leftover technical things. In particular, we're going to talk about unmeasured confounding and quantifying uncertainty. And so sort of the summary here is that everything that all the weighting techniques we discussed last time work on what's called measured confounding or measured non-differential or differential non-response, which is that you see the covariates with respect to which people are not responding. And so today it's partially going to be what can you do if you don't observe that? Then we're going to look at data collection, sort of case studies beyond polling, in particular ratings and recommendations. And then we're going to end with sort of a very quick run through, one slide each, on a bunch of other topics in data collection. And sort of this is partially just so like y'all are aware of things and like know what to look at in the future. Partially also as sort of the last few weeks of the lecture, we have a bunch of this grab bag of topics that I haven't finalized what we're going to cover. And so I'm thinking throughout the semester, I'll just do like one slide on a bunch of things I could cover, and then I'll do like a poll or something near like middle of the semester, near the end of the semester, to see which of these topics y'all want like a full lecture on. Okay, and then we'll end with just a summary of the entire module. Okay. Are there any questions about the plan for today? Okay. So so let's start with unmeasured confounding or unmeasured differential non-response or selection bias or whatever you want to call it. So in the last lecture, weighting really helped us deal with what happens when you have selection biases that you can measure in some sense, right? So like the example is, let's say response rates and political opinion are both correlated with educational status. But education status is something that you can like ostensibly ask for in a poll, and like hopefully people will respond. You can also roughly guess at the voter distribution of sort of like education status and the distribution of who's going to end up voting or likely to vote. And then you can use all the methods that we talked about last time to sort of correct the difference between who's responding to your poll and what's the population that you care about. So I mean that's like the 3-sentence summary of last time. Now, what if response rates and opinions depend on something that you don't observe, or something that you don't know the population distribution of, right? So what can you do? And for example, there's evidence that this is exactly what's happening in the United States more recently in polling, especially around the 2020 election, that there's sort of something called social trust, that people with high social trust tend to both respond polls and vote against Trump. And that's like something that you can't measure in a poll, like how much social trust someone has. And you also can't look at the distribution of voters. Like you can't also, like it's hard to measure the distribution of social trust amongst voters. In this case, there's sort of, first of all, there's bad news, that there's like very little you can do to try to recover sort of like a single answer, right? So last time we talked about a bunch of techniques that like tried to get at a single answer of what the population believes using data in which there's selection bias. And different techniques will get you different answers, but at least each technique will get you some answer. Here, it's really hard to do that unless you make a lot more assumptions on what the unmeasured sort of the unmeasured non-differential response is. But like with some of those assumptions, you can at least like sort of try to recover like a range of potential answers. You can try to quantify your uncertainty for like, under this assumption for how bad the problem is, here's how much it would affect my answer. Okay. Are there any questions about that before I dive into the setup and sort of try to derive a few things? Great question. So the question is how much of these like unobserved covariates can be derived from the things that you observe, right? So for example, maybe social trust correlates a lot with education, and education is something that you can observe. Yeah, so certainly if, if there's some concept that is unobserved, but for which, this is happening, but this concept is very much correlated with things that are observed, or like, even like multiple things that are observed, then yes, you sort of, you can basically sort of, for prediction, for just recovering the point estimate, you can just treat it as observed because it'll just show up, sort of like the weighting techniques on those observed covariates will correct for the problem. That's certainly true. And so sort of in the setup that I'm going to talk about now, I'm going to pretend that like sort of, I'm going to say that there's something unobserved and like ignore all the other covariates, but you should think about that as that's like the unobserved part left after, sorry, my mask keeps falling. That's the unobserved part that's left after sort of you have all the observed things and like sort of you correct for, so it's like the part that's orthogonal or that's missing even after you correct for all the observed things. And so the evidence is that that's exactly what's happening in the US, is that there's like sort of even after you like correct for education or socioeconomic status or so on, that there's this like leftover residual social trust thing that like doesn't show up in any like demographic covariates. Okay, so here I'm just gonna like try to walk through a very simple setup that like, for example, doesn't assume that there's like a relationship between the unobserved thing and the observed covariates, but you can like do something very similar with what I'm gonna do with like if there's a case that there's some correlation. Okay, so in this simple setup, I'm just gonna assume that there's a single binary covariate U that each person has that, same thing as last time, correlates with both the opinion of interest and the response rate. Now, unfortunately, we don't observe U for any individual. And for now, we're going to make the assumption that U is the only unmeasured confounding, that AJ is uncorrelated with the true opinion given U, but we don't have U. And so this is very similar to the assumption we made last time, that sort of given the covariates, response rates and the opinions become uncorrelated or non-independent, or independent, but without that covariate, they are correlated, right? So it's the same exact assumption as last time, but now it's just something on something that we don't have. Okay, and so you have an estimate y hat, which is just, for example, the raw average of responses. Or you could also think about it as the average, like your point estimate, your average after you do all the weighting techniques that we talked about last time on the observed covariates. So like y hat is what's left. Okay, so what can you do? The idea is to make assumptions on how bad the unmeasured confounding is in terms of like quantities you can reason about. And I'll talk about what quantities you can reason about later, or like in the next slide. But so sort of the idea is to just map uncertainty in like quantities you can reason about to see how much it affects your final answer. And sort of stepping back, I do want to emphasize that this technique is something that, I'll talk about this in a little bit as well, is, definitely you can use it for like in machine learning models for like inference. And I think in general, quantifying the let me just put on a different mask. This keeps slipping. Okay. Yeah. So where was I? Yeah. So I want to emphasize this idea of just like quantifying your uncertainty in your answer based on like assumptions, like sort of by like sort of stress testing what happens if your assumptions are failing. So like for example, the assumption from last time is that all the confounding dependent on covariates that you have. So this like general idea of like stress testing how bad your model can be if your assumptions are failing is something that's like often like quite easy to do and is like very valuable when you're interpreting your results. So it's very valuable in just like being able to like if your like confidence intervals are just really really wide, and by confidence intervals I don't mean like just like the standard statistical whatever, like just like your like uncertainty over like how useful your model is really wide. If your assumptions don't hold exactly, then like that should matter for what you're going to do with your model. And so like this like general idea that I'm going to walk through just for polling is something that you should think about using in real life. Okay. Okay. So let's go through the notation and try to derive sort of mapping uncertainty in something that you can reason about to uncertainty in your final answer. Okay. So I think this is slightly different. I think most of this is very similar, or the exact notation as last time, but I just want to be sort of use like simpler notation for what we have now. So let P1 and P0 just be the true population fraction of the people with covariate 0 and covariate 1 respectively. Now let P tilde superscript be the population in that actually responded. So your sample fractions for P1 and P0. Okay, so now the thing that you truly care about is sort of very similar to last time, or exactly the same as last time. It's the weighted average of P1 times the sort of the mean opinion for people for which U is 1, plus P of 0, or P of 0 is equivalently 1 minus P1, times the sort of the opinion, the average opinion of people with U equals 0. This should all be exactly familiar from last time. Are there any questions here so far? Okay. Now, y hat, if you have like a billion respondents, what it's going to converge to is something very similar, but you just replace the p's with the p tildes, right? That's what the notation meant. Yeah. So to repeat what I said, it's like y hat, like your actual estimate. If you just like sample a billion people, like in our notation, we're just going to say that it converges to the or actually, sorry, not so actually what I said was false. Well, you'll see in a little bit that it wasn't false, but it's not trivially true. So instead, what p sort of y hat will converge to is laser pointer. Okay, is P1 tilde. So the population, so sort of the fraction in your sample that has U1, and this is going to depend on the response rate. So if the response rate of people with U equals 1 is really low, then P1 tilde is going to be really small compared to P1, right? So what your estimate is going to converge to is P1 tilde times this quantity, and this quantity is the mean opinion of people such that U equals 1 and the fact that they respond, right? Because y hat, like my actual sample estimate, is the expected value of the opinion given that people are responding to my poll. And so that's going to equal p tilde 1, which is the fraction of people with u1 that respond to your poll, times the mean opinion of people with u equals 1 and the fact that they respond to the poll, plus the same thing with p0, or 1 minus p1, because we assume they add up to 1. Any other questions here? I really want this to be clear, sort of like the difference between the two, like, what we have and what we're trying to estimate. Yes. Yeah. So the question is, in the last lecture, I had A for the response variable. Or so A in the last time was whether they responded, right? And Y was what their actual opinion was, right? And that's exactly what I have here. A is whether they responded, and Y is their opinion, right? And so my sample estimate is going to be the mean opinion of people who respond. And I can break that down by just splitting sort of, in probability, you can break down expectations by by conditioning on like u equals 1 and u equals 0, and then just do a weighted average. So yeah, so this is just like rewriting this in that you can first do this weighted average for people who respond. Or sorry, first you can do this average for people with u equals 1, and then you can do this average for people with u equals 0, and then you can add them up. Now, of course, I mean, this is these values are something that we don't have access to, right? Because u is unobserved, we actually don't know what p tilde is. We don't know, so sort of, we can't actually like break it down like this in the data, but this is what it like theoretically equals. Are there any other questions here? I'm not going to move on until there's one more question. I'm just going to stand here. Okay. Yeah, we don't. So the question is, we don't know u, and so we actually, so we do observe y hat, and y hat theoretically equal, like, can be broken down like this, but we can't actually break it down with the data we have. Exactly. Because we don't, in the data we have, we don't know p tilde, and we don't know for each person whether u equals 1 or 0, and so we don't know which of these two groups, which of the two green groups they would belong to. Exactly. Any other questions? Okay, so the question is, what's the difference between u equals 1 and u equals 0? So this is the same thing as just like a covariate from last time. So you could think of u equals 1 as someone who graduated from college, u equals 0 as someone who didn't. But I'm just using u's instead of x's is because it's unobserved. So last time I used x for covariates that you would observe. Now I'm just using u for unobserved. But it's the same exact thing. Any other questions? Great question. So the question is u something that we don't, is it like an to quote Donald Rumsfeld, is it an unknown unknown, or is it a known unknown, right? Is it like something that we know exists, but we like can't exactly we don't know, we can't observe for each person, or is it something that we just have like no idea what it is? Sort of, I think it's a mix of both, in that sort of what I'm going to talk about right now is like, in a little bit, is like, what if you know that like an idea, like sort of like something like this is out there, and you know, and you can, or like you can make assumptions on like how bad it is, but you just don't observe it for each person, and so you can't like exactly pin down how it affects your answer, right? So like in some sense, it's like something that you can make guesses about at the population level, but you have no idea at the individual level. Any other questions? So the question is, so you won't even know whether it's categorical or numerical. I mean, for now, let's pretend that we do, like, let's pretend that we know that there's like just this like U that's like binary, you know, high social trust or low social trust, or so on. I mean, there's like, you know, you can get as fancy as you want here. Well, the captions are really bad today. I should just turn this off. Okay. Anyway. Yeah, it's probably more distracting than I shouldn't have pointed this out. Okay, anyway. Yeah, so it's yeah, so like for now, let's just assume that it's binary and you know it. I mean, if you for example really think that there's like 3 or 4 levels or like multiple levels on which like this unobserved thing is happening, and you can make assumptions on like, so like I'll get into this in a little bit, but ultimately where we're going down is we'll make a little bit of assumptions on how much U matters. And so if you think that there exists some unobserved thing out there in which like there's 3 distinct levels, like there's like high social trust that is like really likely to vote for Biden and is really likely to respond, there's medium and there's low social trust. Like if you think that there's something out there in 3 levels and that like those 3 levels behave very differently, then you might want to do what I'm doing, but with like, you know, U with 3 levels. Or same thing as continuous. If you think that there's like some continuous covariate out there where like it truly does matter continuously. But like I would focus on that a little less, is because like sort of all we're like sort of we're just like stacking on assumptions right now. And so like your precision of your answer is like sort of if you're like really thinking about U equals 3 levels or 4 levels or whatever, you're like probably focusing on the wrong thing. That's like a level of precision that you like don't even have. Like you should worry about like the high level uncertainty quantification. Any other questions? No. So okay. So the question is why do we only have a combination of P1 times U1 and then P0 times U0? And so this is so sort of like what I wrote here is sort of for those of you who've taken a probability class that covered this, is just like the law of iterated expectation or something. It's like this is just like a mathematical fact that if you have the expectation of some variable given some other variable, you can just rewrite it as, or like just like an expectation of some variable. So ignore AJ for now. You can rewrite it as conditioning on UJ equals 1 times the probability that UJ equals 1 plus that condition on UJ equals 0 times the probability that UJ equals 0. And so like maybe to like say this in words with like an example, is the mean opinion of a population is the same thing as the mean opinion if you graduated college times the fraction of the population that graduated college plus the mean opinion if you didn't graduate times the fraction that graduated. And so that's just exactly what this is doing. Any other questions? Okay, so yeah, so the question is why did I do the limit notation instead of the equal sign? And that's just because I wanted to sort of, if I did the equal sign, then I couldn't do this expectation. So in sort of this expectation is only going to be true if I have 1 billion people. If I have only like 100 people, then like they also have random opinions, right? Because what if I just call the one random person who like has a different opinion than everyone else with the same covariates. And so there's randomness not only in the population fraction, but also in the opinions. But I want to like ignore the randomness in the opinions for now. Any other questions? Okay. Okay, so here's the insight on like why we can do what I'm about to do in the next slide. Is I wrote these green things as differently, but it turns out these green things are exactly the same. Sort of, so let me spell this out. So you have, on the left-hand side here, you have the expectation of the response, given that, you know, my covariate is something, and given the fact that they responded. And on the right-hand side, I have the expectation of the response, just given what their covariate is. I claim you can drop this, like the fact that they responded, because this is exactly the assumption I made on the previous slide. This is exactly the assumption we made in the last lecture, which is given what group someone belongs to, given whether uj is 0 or uj is 1, their opinion does not correlate with whether they respond, right? So this, the fact that this is equal to that is just like this sentence in math, right? Like the fact that they responded gives us no more information on their opinion than just like knowing what group they belong to. Now, we don't know what group they belong to, but like we're not worrying about that yet. I'm sure this doesn't make sense. So I'm not going to move on until there's 3 questions. I'm not strengthening anything. I'm rewriting what I said earlier. So what I said earlier is, given like education, like within the people who went to college, whether you respond or not is not correlated with what your actual opinion is, right? And within the group that didn't go to college, whether you respond or not is not correlated with your opinion, right? Now, like if you don't use education, like if we don't use education, then they are correlated, right? So like maybe more educated people or higher social trust people are more likely to respond and have a different opinion. But given that you have high social trust, you're equally likely to respond to the poll whether or not you support Trump. That's what this is saying. Yeah, great question. So the question is am I explaining or am I assuming away like the shy Trump voter hypothesis, which is people who supported Trump were less likely to respond to polls? And here it's sort of, it can go either way depending on what U is, right? Or like what the exact causal mechanism is. So if the exact causal mechanism is this like elusive category called social trust, which like if you are like less likely to like, you know, think we're all one big community and blah, 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 and like, you know, you like trust government and whatever, if sort of if you have high social trust and you're more willing to respond to polls and, you know, not vote for Trump, if that's the mechanism for why there's like shy Trump voters, it's not that they are embarrassed of voting for Trump, it's really that like they're both correlated with social trust. If that is the hypothesis, then you being some like measure of social trust, yes, that explains that away. If literally like the mechanism is like literally I do not want to tell people I support Trump, then like you being education or social trust or whatever would not, like, right, this assumption would not hold. So it's very dependent on what you consider this unmeasured confounding to be. But sort of in what I'm about to talk about, it almost doesn't matter because like we're not trying to pin down exactly what U is. We're just trying to see like how much it could affect my final answer. And I guess you and you. It works for like how many ever you want. Yeah, so you can definitely generalize what I'm saying to like U's with multiple covariates, I mean like multiple levels or continuous or multiple U's, or like even U's that correlate with like known covariates X's. And like the math is extremely similar. But I just didn't like want to walk through it in class. Can you repeat that? Or like, can you like, like so the question is like, what if there, or like my interpretation of the question is what if there's like multiple unknown covariates and they like correlate in some weird way that's unknown? And you could like, another way you could just think about that is you can just collapse that into one giant covariate, right? In which has levels like the number of levels of U1 times the number of levels of U2, right? And then it just becomes like one bigger covariate. And so yeah, so the same, like that's not really a complication. Yeah. How do you explain that you are understanding an unknown correctly and that it's actually something that goes over time? That's a wonderful question. This is what I'm going to talk about in the next slide. Okay, but oh, sorry. Y'all aren't doing your jobs at telling me to repeat the question. Okay, yeah, so the question is like what do I actually do with this, right? Like how can I use this for like the future? Because like the whole point is like I don't know you, and yeah, great question. Yeah, so the question is given U is unobserved, like why, why make this assumption? Like why I sort of, yeah. So I think there, the sort of the answer is that just because it's unobserved for each individual doesn't mean that you like don't know that it exists in the population, right? So like you don't know exactly how bad it is, but like, you know, and I'll talk about this a little bit in the next slide, but like, you know, suppose you can guess, like, or like, you know, you can make, you know, actually, yeah, let me just talk about this in the next slide. No, yes, exactly. So I'm claiming the green things are equivalent to like sort of across these two lines. I'm not claiming the two lines are equivalent because P1 is not the same as P tilde. Any other questions about this slide? Okay, so I think that was at least 3. So let's just like do some algebra now. So if we just, okay, so now if we just make the substitution that I said was equivalent, y hat, or what y bar is the same as it was last time. Y hat converges to almost exactly the same thing, just p's are replaced by p tildes. Now you can do some algebra and rewrite it such that y hat converges to y bar. So I'm not going to go through the algebra, but sort of You can do a little bit of algebra. You can see I've uploaded the notes, but sort of the end result is y hat converges to y bar plus this error term. And what is the error term? The error term is the difference between p tilde 1 minus p1 times the difference in opinion, the average opinion by people who have u equals 1 and u equals 0. Right? So it's the sort of by how much does my population differ from, or like my sample, like, you know, in the limit differ from the population I care about, times how much does u actually matter for the opinion? How much is u actually changing whether someone supports Trump or not? And then sort of the uncertainty quantification thing is, you know, hopefully these two quantities are something that you have some guess about at the population level. So you don't know for each individual whether u equals 1 or u equals 0. But that these quantities are something that you like can guess at how bad it is. Or you can make like a range of assumptions, like if it was this bad, this is what this is how it would affect my response. And then that just lets you quantify how far y hat can be from y bar, even if you had 1 billion people. Now, on top of this, there's like the uncertainty that I'm not talking about, which is like the sampling uncertainty, and like the 10 people you called could just be weird. But sort of like, yeah, you could layer that on top. And what's also nice about this is if either the population looks like the sample looks like the population, or if u doesn't matter in the opinion, either like they don't both have to be true. If either is true, then you have low error. You only have big error in the case where there's exists a u where both there's a large differential response and the opinion it matters for the average opinion. Yeah, so okay, so I'm gonna do my interpretation of your question, which is like, is it easier to make assumptions on these things than it is to make assumptions on y hat? Yeah. So my claim is that it's easier to make assumptions on these things because the sort of y hat is, I mean, like you could just like, you know, make up, oh, you know, my like in the sample it says 45%, but I'm just gonna like make up that it's like, you know, anywhere 10 points in either direction is fine. But like I would at least claim that it's for like, you know, for those of you who've done like what's called like Fermi problems, this is like sort of you have like a really complicated estimate that you care about at the end, and it's often easier like if that complicated estimate is like made up of constituent parts. It's often easier to reason about the constituent parts than it is to like reason about this like complicated estimate at the end that like depends on 20 things. And so that's exactly what we're doing here, is that the claim is that it's like easier to reason about, for like, you know, let's just say that I think that at most high social trust people and low social trust people have a difference of opinion of like 5 or 10 points on average. So, you know, it's at worst, it's 55 times 45. And at worst, you know, I like AJ is like, it's sort of like whether you respond if you have u equals 1 and whether you respond by u equals 0 is like, this is what they look like. And depending on what they look like, I can sort of derive like a p tilde minus p1. And my claim is that it's easier to reason and defend that than it is just to like make up that like y hat is true within 10 points. And so sort of going back to the question on the previous slide, which is, okay, so this seems like something you can do in hindsight, where, you can explain in 2020 polls that like, this was the difference, like sort of unobserved confounding, but how can that help us in the future? So how exactly that can help us in the future, and like part of why I claim it's easier to reason about this than y hat, is like, suppose in 2022 you think, like my polling methodology got better, right? Like polling methodology is always getting better. And so I did some things to try to reduce this difference, p tilde minus p. But at the same time, maybe the country is polarizing more, and like it's polarizing more on things I can't observe. And so this thing is getting bigger. This difference is getting bigger. And so you can try to reason about, okay, so like, how much does the fact that I reduce this help? And how much does the fact that like this is getting bigger hurt? Yes, yes. Yes, okay. Yes, okay, right. So the question is I don't know the orange part and I don't know the green part. And I'm using those things to quantify like how much like I could be wrong. And so like I'm doing some uncertainty quantification based on things I don't know. And yep, that's exactly what I'm doing. The claim is that's still worth doing because it's easier to make assumptions on the orange part and the green part than it is to like directly make some claim about like how bad my y hat can be. That the orange part and the green part are things that you can use like your domain knowledge on. Like, pollsters can sort of guess at like how bad my population difference is and how bad my mean opinion are. But they like, and so if you, and especially if this is like, especially if we're in the more complicated scenarios that you were talking about, like y'all were asking about, like U is like, non-binary and, it correlates with your known covariates and things, is that it's much easier to break that down and make assumptions on each part than it is to just like throw a number for how bad y hat can be. Yeah, so the question is what if we don't know that p tilde 1 is bigger or smaller than p1? And yeah, exactly. So sort of for each assumption you make on sort of the orange part and the green part, you get some answer for like how y hat relates to y bar. And so if you think, for example, that the range, if you truly don't know whether, I'm going to continue using the education example. If you continue like, and like, let's suppose for this case, education is unobserved, or you can think about social trust or whatever. If you like truly don't know whether people who went to college are more likely to respond and less likely to respond, then like the range of like p's that you like, the range of the orange that you should like simulate should be negative through positive. But if you have a pretty good idea that those who went to college or those who have high social trust are more likely to respond, then you should like guess that p like sort of this subtraction p tilde 1 minus p1 is positive, but like, there's some range it could be. That's yeah. I think to first. Okay, so the question is if I'm the person going out and collecting data, is it reasonable for me to think that the orange term is what I can control? I just realized orange and green is not great for red-green colorblind. Okay, the sort of the P's term is something that you cannot control, or the P's term is something that you can control, and this expectation term is like the world, like something that you can't control. I think the first order that's correct is that your polling methodology, like who you end up calling, really does affect the first term. I don't want to concede that the second term is something you have no control over. So sort of time permitting later on in this lecture, sorry, I don't have my watch today, so I have to look at my phone. Okay. Time permitting later on in the lecture, I'm going to talk about how like the questions that you ask can like deter, like sort of, change the measurement that you have, right? Sort of like maybe, I mean, like, yes, in some sense, this is like actually, no, yeah, I don't want to get into that now. Yeah, so I think the first order that's correct is that like the P's are really something that you have under your control. Any other questions? Yeah, exactly. Yeah. So the question is like, how would you actually use this? And sort of the question is like, would you like assume different values of P or like, yeah, different values for these unknowns and then see how it affects your answer? That's exactly what you would do. So you could like imagine a plot like in, like in a scientific paper or like, and like communicating your results to, like your manager or whatever, that if I'm in a world where there was like really bad differential non-response, here's like what the answer would be. And if I'm in a world where there's like moderate, here's what the answer would be. And like the hope is that you can either convince people what world you're in, or you can convince people that it doesn't matter what world you're in, the decision you make will be the same thing, right? Because like y hats are not affected by that, right? Like pretend like like one of these, but you don't know the other, right? Then you could say is like it doesn't matter how bad, like if this green term is small, it doesn't matter how bad the orange term is, like you're still going to do the decision I want you to do. Any other questions? Okay, cool. Okay, so sort of like the last thing I want to say here is like similar to what I just said, which is in data science, we often care about what's called causal inference. So you often, and we'll get into this later on in the semester, I'll hopefully have a lecture on this, in which you often care about like how much did like this very, like the fact that this, like, this person was treated or this person got this price or this person, whatever, how much did that actually affect the response variable I care about, as opposed to just like correlations, right? Like the fact that they opted into the survey correlates with their response, but like sort of, yeah, like the fact that they got this coupon actually like led to them buying something, whatever, right? Or for example, you can think about what is the causal effect of private high school on college success. And like it could have a causal positive thing because like, private high schools are richer, they have like smaller class sizes, and so you learn more, blah, blah, blah. Or, you know, maybe whether or not you go to a private high school depends on your parents' wealth. And like parents' wealth in college means that you don't have to work you don't have to work a job. And so you have more time to study and so on, right? And so distinguishing between these two things of like whether it just correlates because of something else, like some like unmeasured confounding, or yeah, the unmeasured confounding is you might not know parents' wealth. And so if you're like training a model to try to figure this out, it really matters whether like private high school causally improves college success, or just like correlationally improves college success, because that, for example, matters in, do I subsidize people going to private high schools? Do I do voucher programs, things like that, right? And it turns out, sort of almost exactly the method I talked about in polling, you can do something like that to quantify unmeasured confounding and the range of effects in these type of models. And there's some really nice papers. I think one of them I put in as the suggested readings for today, I'm not sure, that do exactly this. And so this is not just like a small idea that's like specific to polling. This is like a far more general idea, is that like there's like nothing you can do to correct for unmeasured confounding, but there's a lot you can do to figure out like how much it likely matters. Okay. Any other questions on this? Or like polling in general? Because I mean, we're gonna have a guest lecture next week, but sort of, I think this is like the end of like sort of the polling part of the data collection module, besides the guest lecture. Yeah, so the question was to repeat the last thing I said. And yeah, so it's like just like in the polling example, like in the last lecture in weighting, like I literally gave you mechanisms that, you know, you have some y hat, like you have some mean response that actually responded. But if you like plug in this equation and like, you know, you're doing this in the homework, you get a different estimate, like a mean estimate of what the population thinks, right? And you have data for that, you can just like do it. What I talked about today, like you can't go that far. Like you can't actually say, like, you know, here's the data I have, here's a technique, here's my answer. You have to make assumptions on if the population looked like this is what my answer would be. If my population looked like that, instead my answer would be like that. And so this like general idea, and so this general idea is also in other settings, including this causal inference setting, which is like I can't do anything about the fact that I don't have certain data, right? Like the fact that in this data set I don't have parents' wealth is like it's like a fact of the world. I can't do anything about it, but I can like try to figure out how much it matters. Any other questions on this? Okay, so let's see. So less than 20 minutes. So I'm probably going to be very quick. In this part, I'm going to skip some of the things I talked about. This is, I mean, this is great. Like y'all asked a lot of questions. But whatever I don't get to, I'll do updated notes on the slide and post on the website. Okay, so so far we've talked about explicit opinion collection and polling. The same challenges are going to apply in many other settings. So I mean, there's, you know, I'll talk about some similarities in a little bit, but there's also a lot of important differences that matter. And it's like, what are some of these differences? Often you don't care about the absolute opinion, but you care about relative opinions. So like this could be relative over time, or like item A versus item B, right? So like if someone cares, like sort of which of these two items do you like more, is more important to know whether like 55% or 53% of the population likes item A. In practice, especially for like recommendations and pricing, personalized recommendations and pricing, you don't care about the mean opinion across the entire population. You care about what's called heterogeneous opinions. You care about like how opinions might differ across like one person or another person, or one group of people or another group of people. And then you often have, like, often you don't just have data on like explicitly asking people. You often have like implicit data based on just like what they've done and what you've collected. So like Netflix, for example, like very few, like actually they got rid of it, but like sort of they used to like really push star ratings on people, right? They used to really ask you how much you care about like how much you like this movie or not. But like actually, let's just do a show of hands. How many people have in the last 2 years submitted a rating for how much they like something on on Netflix? Right? Like almost like basically there's like 2 people, 3 people raising their hand in the entire classroom. Um, that's just like a rare thing to do, but like that doesn't mean Netflix doesn't have data on you, right? Like Netflix has your entire watch history. It knows when you paused, it when you stopped watching, it knows when you continued, it knows like whether you watch the next episode. It knows a lot of things about what you watched and how you watched it. And all of those things give them like give them information on whether you liked the item or not. And a lot of those things give them information on what thing they should recommend to you next. And so that's another form of data collection. It's not explicit. They're not asking your opinion, but they're using data exhaust or implicit data to figure that out. Okay, and so I'll briefly discuss some of the challenges related to what we talked about in ratings and recommendations. And because we have like 15 minutes, it's going to be very, very brief. Maybe some of this will be in next time. Okay, so I think everyone's seen rating systems. You know, after you use anything on an online marketplace, you're going to be like often you're asked to rate things. A very common problem in all of these rating systems is what's called, and I talked about this briefly a few lectures ago, is what's called rating inflation. This is a form of measurement error in which basically everyone's getting 5 stars all the time. You know, like a 4.7 on Uber in the United States is way below average, like to the point where the driver might be on probation or something like those lines. This is a really funny XKC on how to interpret ratings, or at least I think it's funny. Okay, so like why do ratings inflate and what can you do about it? So there's a lot of hypotheses, some related to like selection bias, differential non-response, and some related to measurement error, which is either someone's lying or what people think a rating is very different than like what you want them to think it is. You can have explicit pressure. You can have implicit pressure, right? It's like I just don't want to ruin someone's livelihood by giving them 3 stars and putting them on probation on Uber. And so that leads to like multiple avenues that either translate to selection bias or like measurement error or just like lying. And so inflation in general could be considered as like something that's a difference between the sort of the thing that you care about and the thing that you have, sort of measurement error, right? It's that the quality scale doesn't match up well to the rating scale. And in particular, if you have inflation over time, that means this like mapping between the construct and the measurement you have is changing over time, right? Is like a 4 stars 5 years ago meant above average, 4 stars today means below average. Why does it matter? I think this is one of the homework questions on the conceptual part. Okay, so what can you do about it? You can try to reduce some of the pressure. So for example, you can like make ratings less consequential if people aren't worried about like ruining an Uber driver's job or life. If giving them a bad rating, maybe you're more likely to give them a bad rating for like things that really don't matter. So in the homework, I ask you to read a paper that does a form of weighting. They don't say it in these terms, but it's almost exactly a form of weighting to tackle the selection bias. And then you could also try to directly, and this is something I don't have time for, yeah, definitely don't have time for, is you can also change the rating scale. So you can also try to change the mapping of what people consider a 5 stars to 4 stars. And that might be confusing, so maybe I'll give you like a 1-sentence summary. So I won't talk about the experiment. But what I can do is, so like, suppose you have a numeric 5-star rating system, right? It's like 1 to 5. At this point, like especially on Uber, like 5 stars means like anything but like this person like tried to kill me, right? Like you're like, at least in the US, you're like almost never going to give someone 4 stars or below. And so like same on this, like this freelancing platform is like their status quo was something very similar to this. But you can also, instead of like, if you're the platform, instead of giving people 1 to 5 stars, you can tell people what each level means, right? You can tell them, you know, you can have them select an adjective. Like you can say, this was the best freelancer I've ever hired, or this was like above average, or this was good, or this was below average. And what we did in this experiment is we just positive skewed the ratings. So like a equivalent of a 5 out of 5 was this the best person I've ever hired or the best possible freelancer. The equivalent of a 2 out of 5 was this person is good. 1 out of 5 was mediocre, and so on. And so the question is can you induce people to like relatively say this person is 2 out of 5, but like they think that they're saying this person is good. And so this is like trying to correct the mismatch between the construct that I care about and the sort of the measurement that I have. And sort of turns out it works. Turns out if you do something like this, you can move people from like 80 to 90% 5 stars to like 30%, like give the best possible rating. Okay, I'm not going to talk about this. I'll talk about this next time because it has to do with recommendations. And next homework is going to talk about this quite a bit. Let's see. How much time do I have? Oh, I have like 10 minutes. Okay, cool. Any other questions on that admittedly very quick run through ratings and recommendations? So I just wanted to leave some time at the end for like homework questions and things like that. Yeah, that's a great. So the question is like that like very quick experiment I walked through in which like if you do adjectives like in like 6 months, are people just going to learn that like you should just give everyone the best possible? We tested for that, so like we kept the experiment alive for like several months, and like it didn't seem to have a huge impact, mostly because like there were new clients coming onto the platform all the time who like weren't used to that, but like we're used to 5 stars from like Uber and Lyft. But yeah, that's a great question, and it's hard to know, and it's like oftentimes there's other tricks you can do, and so like sort of we started looking into things like that, which is you can like what if you just like force comparisons, right? So like you force people to say this freelancer was better than that other freelancer that I hired. Like there's like you know physically no way for them to inflate that because they just are forced to choose one or the other. So you can look into doing like you can look into like taking away choice from the raters. Okay. So now I'm going to spend about a minute each on a whole bunch of other topics in data collection. And like, I just want this as an advertisement for like a poll that's coming in like 5 weeks, 6 weeks for like what y'all want me to cover at the end of the course. Okay. So the first thing is, what if you want to ask about a sensitive attribute? Like, what if you're an insurance company who wants to measure the the percentage of your like people that you insure that smoke? But of course, if you just ask everyone that you insure whether they smoke, like everyone's going to be worried. Like all the smokers are going to be worried. If I say yes, are my insurance premiums going to go up? Right? Like no one wants to tell you the truth for whether they smoke. And so the goal is, as the insurance company, you don't care, or I mean, maybe you do, but like for the purpose of this exercise, let's say that like you really care about the percentage of your population that smokes. So you like, you know, you can do like accounting, you can do risk assessment, You can do like year-on-year estimates, but you don't, at the moment, care about whether individuals smoke because like you don't want to raise individual people's premiums. So how do you collect data such that you get like the overall population number correct, but you don't actually learn anything about the individuals, so that like individuals can like be confident that you're not going to use their answer against them. And so the idea here is that you add noise to each response. So for example, let's say that you tell each person, roll a 6-sided dice and don't tell me what the answer was. But if it's a 1 or 2, lie about whether you smoke. So tell me the opposite. And if it's 3, 4, 5, 6, tell the truth. Right? So if people actually, so for each person, if they tell you they smoke, you have no idea whether they were lying because they rolled a 1 or a 2, or whether they're telling the truth because they rolled a 3 to 6. And so, I mean, yes, I mean, like if they tell you they smoke, you're like slightly more sure that that person smokes, but probably not in enough in a way to actually charge them more, right? Because in hindsight, they could just be like, no, I don't smoke. I just like rolled a 1 or a 2. But at the population level, you can easily figure out the truth, right? So if Y percentage of people smoke, you know that, or if Y percentage of people say they smoke, then you know that that's because sort of 1/2/6 of them said it because they don't smoke and they lied, and 4/6 of them said it because they smoke. This is a single equation with one variable, with one unknown, and so you can figure out what X is. And so this is what's called, or like similar ideas are what's called differential privacy, which is just like you add noise to individual responses so that the overall is something that's accurate, but you don't learn anything about each individual. Similar ideas are used to collect and share data at like companies like Apple, and as well as the entire US Census. Okay, so cool, okay. So the next is using bias data. So the world is, of course, full of historic inequities. For example, some neighborhoods are over-policed, and so data about that neighborhood will detect more crimes in that neighborhood than other neighborhoods, just because there were more police officers there to like create crimes or to arrest people. Every possible opinion is expressed on forums like Reddit, and like that's what's used to train natural language processing models. If we, there's some universities now who are getting into the sort of who historically have used like machine learning models to try to predict how likely someone is to succeed at their university. But if their university has a bad culture, or in the past has like not like well supported people from from underrepresented minorities, or like has not provided good financial support, then like who has succeeded in their university in the past is not a great indicator of who can succeed, right? And so if you use that type of model, so if you use models trained on this data, you're going to often reflect and amplify these biases in the decisions you make. And so this is a plot from a paper which sort of like in so natural, I'm not going to sort of describe how it's done, but in natural language processing, you train words based on like you train vectors for each word based on like historical data that you might find on the places like Reddit. And it turns out if you do that, like this is how like all speech recognition, all like text to speech, everything works at like searching works at Google and everyone nowadays. If you do this, what you're going to find is sort of biases in the real world are reflected in the data. So like your vector for what you think is like a housekeeper or librarian is closer to the vector for women than it is to the vector for men, right? And so now if like Google is making decisions of like sort of search answers on this when like someone types in computer scientist, then that's going to like amplify those biases if you're using these embeddings. And so there's many techniques to audit and mitigate such biases, and I can talk about that. I'll do 10 seconds each on the next few. So far we've talked about eliciting binary opinions, right? Do you support Trump or do you support Biden? You could also think about supporting far more complex opinions, like what is your optimal US budget? Or like, how much should Cornell Tech spend on like a park versus like better Wi-Fi or whatever like things you would want, right? Like how should it split up $2 billion or $2 million over like these 10 projects? There's a lot of you can't ask people to rank every option because there's like many possible ways you can spend like $2 million across 10 projects. And so there's like a lot of techniques to like, ask people about more complicated opinion spaces and aggregate their answers into something meaningful. And then finally, data dynamics, which is that the world is not static. Opinions change with external events. Your startup is growing and attracting new customers, and so it's a very different company than it was a year ago. Weekends are different than weekdays and so on. And so if you treat each time period as a separate like world, you're going to end up with the same like problem that I talked about in survey weighting, right? Is that if you like think today is different than yesterday, then like I might not have enough data today or this month. And so I might have really bad or noisy estimates. But if I use data from like 6 months ago, that might like not actually apply today. And so how do you aggregate these like opinion dynamics over time in a way to like sort of be somewhere in the middle between those two problems, that you're like leveraging data from the past, but not in a way that's like not respectful of the fact that the present is different than the past. Okay. Cool. So I think that's all I have for today. I'm happy to take questions offline. I'll do the summary next time. Announcements are up here. I guess the big one is homework is due Sunday. We're probably not going to answer questions on EdSTEM over the weekend, but we will be active during the week. So if you have questions, come to office hours, ask on EdSTEM during the week. Guest lecture on Monday, please come in person if possible.